the Scheme programming language was integral to Michael's education. He earned a PhD in computer science at Indiana University under the direction of Ken Dybvig, and he has worked with him on Scheme. He has worked with Simon Peyton-Jones on the implementation of GFC. He has been very active about anything functional. He has done noted work about parser combinator with Matt Might. And after a number of years of postdocs, he joined Yale NUS College exactly at the time where Yale NUS was announced to close. So he switched to the School of Computing, where he's hailing us from today. He has been active in the Scheme community, have been served in the Scheme workshop for twice, and he has chaired the workshop in 2020. And today, he's going to tell us about his idea for future research directions in Scheme.
Thank you. Thank you very much for that. Okay, so it's wonderful to be here. And as Olivier said, I want to share with you some more speculative ideas about future directions for research that could happen in Scheme. And I do want to emphasize, this is very speculative. And second, I hope you steal these ideas. I place no claim on these ideas. I'm presenting it to you because these are ideas that I think need multiple different people exploring in different directions. And as it has been said sometimes, Scheme community can be a little bit like herding cats. Well, for these ideas, that's a good thing, because there's a lot of territory to explore. Okay, to start, I want to give you a little bit of perspective of where I'm coming from. So a lot of my research comes down to the concept of improving programming language ergonomics. And exploring, can we fix the, improving programming language ergonomics. And the fundamental problem is that when I write code, I have some image in my head. But so often the language I'm working with slows me down. Now, some languages slow me down a lot. I'm going to blame certain languages like Java. Other languages slow me down less, such as Scheme, but they still slow me down a little bit. So I want to find those places and improve on them. This leads to applications in a number of areas. This includes applying techniques that will improve domain-specific languages. Because the particular task that you're working with, it's useful if you use a tool that's tuned to that task. This applies to things like metaprogramming and generic programming and macro hygiene in order to be able to write these domain-specific tasks. Macro hygiene is actually rather interesting because there's an ergonomics at two different levels. One is I want to make the process of writing macros easy. And two is I want to make sure that when someone uses the macros, that they can trust that the macros aren't going to do weird things. This also applies to areas such as parsing, static analysis. This also applies to areas of parsing and improving because notation ends up mattering. This also applies to static analysis because it becomes important not just to be able to comprehend the code, but also be able to be guaranteed that the code will be optimized so that we can use high levels of abstraction without feeling a guilt that the performance will be coming poorly. And finally, something we've been working on recently is developing the concept of what we're referring to as fixed point oriented programming. Because a lot of the problems I've run into, the way we end up implementing those is a work list. And writing work lists, frankly, as I will show you, is a miserable experience. And I think that's something we can improve on. Okay, so my inspirations for this, sort of at a meta level of where do we learn how to design languages well. Well, one of the places I want to look at is way back, Guy Steele's Growing a Language. And I'm sure a lot of you have read this. For those of you who haven't, you absolutely should. I will warn you, the first few paragraphs seem a little bit odd, as you can kind of see here. But once you get into it, you'll understand why he's doing what he's doing. But the main thesis of this is that one of the things that makes the Scheme language great is that rather than having a small collection of language experts coming up with what they think the good ideas for the language are, Scheme is a very extensible language, and as a result gives users the opportunity to extend the language and try what they think is good. And through this process, they can see what others have done, they can borrow ideas, and there's this general evolution that allows us to grow a language and discover what actually works. And this ties in well with concepts from the HCI world. This is another book. It is not about programming languages at all, but it is about how you design objects to be used in the real world by humans. It's a very influential text, and for programming languages people, I think it's a text very much worth reading. The main thesis of this text is that in order to figure out how to design something to be used well, there's basically two things you have to do. Number one is you have to actually build it and use it. And number two is when you are building and using it, when you're using it, you want to pay attention to where are the friction points, where are the pain points. Those are things that you can sit down and try to theorize about, but actually doing it is a much more practical element. And you can see echoes of that in the concept of growing a language, because we can try and build the language and then see where the pain points are and try to evolve it from there. I actually have a demo here today. I'm not sure how much you can see that from the back, but these are two cups that I happened to find in a hotel about 10 years ago. So they're a little bit delicate, and they're the only ones I have, and the only way to demonstrate it is you have to have two of them. So these particular cups, if you actually look at them, there's a lot of design that's going into this. First, there is internal ribbing that provides strength, but it also ensures that when they're placed together, that they do not fully seat. That is intentional and combines with the fact that there's external scalloping that looks decorative, but it also provides an air passageway so that when you stack up these cups, the vacuum effect that you frequently have with stacked cups is much reduced. In addition to that, the scalloping along the bottom is positioned just right, so it tends to lock the cups into a position so the handles line up nicely, and when you have a large stack, it forms a nice little spiral, also very convenient and easy to work with. Finally, the handle on the end naturally forces the hand into a certain grip. And I think the design of this handle was based on the concept that this cup would be holding hot liquids. And so with a normal plastic cup, if I've got a hot liquid in it, it will eventually burn my hands. But the structure of this handle, if you'll notice, the tail is such that my hand is not actually touching it. The way this is structured ends up holding my hand away from the cup. There's a slight gap here in order to make the thumb more natural. There's this lever action happening here, so I don't have the cup here. I just lift it up like that. And also, even the thin structure, which I'm sure was also for reducing the amount of material used, but it increases the thermal resistance so that the handle won't get hot because the passageways are so narrow. So these are the sorts of concepts that you meet within the world of design, and I think that's something that the Scheme community is very equipped to experiment and try a lot of these ideas with. Finally, one other inspiration I do want to call out is the works by Tufte. Because within programming languages, it's all about communicating to the human, being able to make the human able to understand, write, develop, debug a piece of code. And all of that comes down to comprehension. So being able to, he's actually written a number of these books. These are his earlier ones, and I think they're more well-known. Being able to look at various pieces of information, and he goes through examples of how people have looked at maps and tried to figure out how to convey quickly and in a way that users can understand well all of the information that needs to be available. In fact, after reading these, I've become a bit of a map collector, and I've actually got a collection up front if you want to take a look at a few different maps, because it is an interesting problem of how do I communicate information. All right, so with all of that said, today I want to propose a few ideas. Two major ideas, and then a smaller collection of other ideas. These deal with the idea of improving the debuggability of languages, in particular designing languages to be debuggable. And the other is first-class continuations as first-class citizens, not just first-class values. All right. As I said before, huge disclaimer here, all of this is speculative. Parts of these slides are going to be wrong. You're going to say, that's not going to work. That's great. Take the ideas, evolve it, do the version that works right. Okay, so it is widely said that debugging is 80% of software development, and if AI is writing some of your code, it's probably a bit more. So that raises an interesting question. If debugging is 80% of development, why aren't we spending 80% of language design focused on debugging? After all, if I'm doing a 10-hour development task, that means I've got 2 hours doing the the programming, and 8 hours doing the debugging. Would you rather I double your productivity at double your productivity at the programming part, or would you rather I double your productivity at the debugging part? Now, there are certain aspects that we see in terms of purity and types that definitely do improve debugging or verification, but frequently it's not really viewed as an explicit goal. And I think that's something that is being overlooked by the programming languages community. Now, when I mentioned this to Will Bird, he did tell me that actually in the game development world, they are very conscious that they want to optimize their debugging process. There's apparently a quote from John Carmack about how if you don't know how to use your debugger well, that's your primary tool. That's what you need to be working with. Sort of like how I would say that if you want to use your editor, your IDE, you want to be able to use that well. But they lift that to the debugging level. Even like when they start up their work for the day, they start by default in the debugger. They don't move to the debugger once they don't program and then move to the debugger once they meet a problem. They start from the debugger. This is secondhand information, so I hope that is accurate. I would go even a step further. Most undergraduate curriculums, I don't think I've ever seen a curriculum that includes debugging as an explicit course. Why aren't we teaching our students this? If this is what's going to matter between spending 1 and 9 hours or spending 2 and 4 hours, this should be a relevant element. Now, sometimes you will have a lecture on debugging tools, but it's usually only one lecture. But it's more important to be able to teach people debugging methodologies. And in fact, I've started to develop one lecture on this. I do not have enough material for an entire course, but I would very much be interested in someone who does have material for an entire course. And if you're interested in what I cover in that lecture, I'd be happy to talk with you about that afterwards. All right, well, that's all great, but what about language design? Can we design languages to be debuggable from the start? Now, I think there's a lot of different directions to go in that way, but I want to propose one example of this to you. So, what are the limitations with existing debuggers? Well, to start with, they're generally considered complex to implement. You know, I think of like, oh, I want to replace the IntelliJ debugger. Oh my goodness, I'm going to have to learn assembly. I'm going to have to deal with interrupts. I'm going to have to learn all of these sorts of things. And that presents a barrier to entry for anyone who wants to like try to experiment with this idea. Maybe I've got one idea that I want to implement, but currently debuggers are viewed at least as complex. However, I don't think they have to be. The second is debuggers are usually an external tool. We see how this can be a barrier to usage. For example, we can see this with the realm of parsing. So in the realm of parsing, you have sort of two categories of parsers. You have the parsers that are an external tool. So these are Yak, or in the Haskell world, Happy. And you also have the parsers that are an internal library. These are things like Haskell's Parsec or like Racket's parse tools. And there's a large divide between these two. When it's an external tool, what happens is developers start to avoid trying to use that. And for good reason, because it's an external tool. I have to go find it, I have to go download it, I have to make sure it works with my current version of the language, I have to integrate it into my build system, I have to learn all of its idiosyncrasies and the command line flags and all of that. Whereas if it's a library, I import, and I can move on. So one of the major limitations with debugging, and in fact encouraging better debugging practices, I think, is that a lot of them are currently external tools. And finally, a lot of them are not extensible, customizable, or programmable. They do have some functionalities, but these are elements that we could improve on. And I hope to demonstrate to you today an example that will improve on all three of these. So in order to do this, I'm going to say, let's try to build the simplest interpreter. And the great thing about interpreters is they can be demoed very quickly. In fact, typically in the very first lecture of my PL course, I try to convince students that they too can write interpreters by live coding one in the first lecture. So we have your standard six-form scheme interpreter. We have literals in the form of quote, variables, lambdas, applications, conditions, and set bang. And I'm going to say we shouldn't be teaching a six-form interpreter. We should be teaching a seven-form interpreter. There's only one more form that has to be added, but this one form gives us a lot of power. The way this form operates is that if I call the evaluator, and during the execution of that code, it runs into a debug statement, it is going to exit the evaluator. It is going to go back to a REPL, at which point I can start to inspect things, and then eventually call continue, at which point the code continues executing. As I'm looking around, I can inspect what is the, depending on the interpreter, let's say I'm doing a CESK machine, I should be able to inspect the code, the environment, the store, and the continuation. This idea of REPLing into the interpreter has been very successful to other applications. Again, in the Haskell world, the Hermit tool allowed people to REPL into the compiler and implement optimizations dynamically and in a live way. And that was able to develop optimizations that we wouldn't have been able to spot before. And you might also notice eval and debug have some very close similarities, both to delimited continuations and perhaps to staged metaprogramming in terms of quote and quasi-quote. I don't know what the exact laws of these are here. That's why I'm proposing this all to you. Okay, so what can we do with debug statement? That's like one thing. What can we do with that? Well, one is if I want to set a breakpoint. Well, what does setting a breakpoint correspond to? It's editing the code. It's inserting a debug statement. Well, what if I want to set a conditional breakpoint? Well, all that means is I'm editing the code to add a condition that tests whether the breakpoint is there. What if I want to set a watch point where there's this dynamic variable, and if this variable ever becomes true, I want to suspend? Well, it gets a little bit interesting there. I'm not sure exactly how it works, but it looks a lot like I'm actually wanting to debug the interpreter itself because I need to include this condition on every step through the interpreter. Then I can start to build up libraries on top of these fundamental ideas. For example, I can implement time-traveling debuggers. How many people here are familiar with the concept of time-traveling debuggers? Okay, about half. So the idea here with a time-traveling debugger is lots of times I'm stepping through, trying to find the point where the bug happens, and I accidentally step one too many. And rather than having to start back at the beginning, it would be nice for me to be able to step backwards. Well, if I have the code, environment, store, and continuation, I can just save those at some point in time, and then later restore them, and I can operate from there. But then once I have that concept, I can implement a form of debugging in the form of bounding and bisecting. So in Git, there's the git bisect command that lets me find the exact commit that introduced a certain bug. Well, if I've got time travel, I can now build a library that says, okay, here's a point where the bug has not happened yet. Here's a point at which the bug has happened yet. And we do a binary search. Has the bug happened yet at this point? Okay, the user's going to have to do some inspection to figure out if they think the bug is before or after that point. And it can say yes or no, and then eventually narrow down to the exact point in time at which the bug happens. If this detection of whether the bug has happened can be automated, if I can provide a predicate, now this entire process can be automated. Which also has implications for things like fuzzing, where you could start to explore, does this path lead to the bug, does that path lead to the bug? And so I hope to have convinced you that with this one feature, this debug statement, which should be relatively easy to implement in a typical interpreter, we can expose to the user a way to build their own versions of a debugger, their own capabilities or libraries, and we can build this ecosystem of tools for debuggable languages. But more broadly than that, even if it isn't this specific technique, I do want to encourage people to consider the debuggability of languages as an important element of that design. Okay, next topic. Continuations as first-class citizens. Currently, continuations are first-class values in that they can be stored in a variable. However, I would contend that currently we are not treating them as first-class citizens. So expressions and values, they can be stored in a variable, they can be inspected, they can be written directly. And this is useful because if I'm wanting to teach someone what expressions are, I can write them down. I can literally show them what an expression is, and I can talk to them about what the variables are that come out and show them those, sorry, not variables, values that come out, and show them what those values are. However, with continuations, yes, they're storable, but there is no way to directly write a continuation. The best you can do is you can write an expression and then grab, during the middle of that expression, grab the continuation that would be implied by that expression. However, it does exist a calculus in which continuations are first-class citizens. They are entirely equal. In fact, there's a formal dual between continuations and expressions. Everything you can do with expressions, you can do with continuations. The two leading examples of this work is The Duality of Computation by Kurian and Erbilin, as well as Call by Value is Dual to Call by Name by Philip Wadler. But there are many other works that have been developed building on this idea. And this calculus, once you develop it, ends up having deep connections to linear logic, sequent calculus, and copatterns. However, the problem with a lot of these systems, in particular these initial papers, is that they're calculi. They're not languages. And calculi, frankly, are very mathematical, and I'm just a poor programmer. And so understanding a calculus is actually kind of hard. I can sit down and stare at it, but I'm always going to be limited unless I can actually try it out and program it. And so what I'm going to suggest today is that just as Lisp and Scheme made lambda calculus accessible to the masses because it provided a way for people to actually experiment with it and try it out and see what it is. And so it's not this weird thing where it's like, oh, okay, so for lambda calculus, you have to do capture, avoidance, substitution, and then you have to understand this equivalences and all this. It's just something we naturally program with and thus develop intuitions with. I'm going to suggest that the same thing should be done for the dual calculi, also known as mu calculi. I do want to highlight there are some efforts in this direction, most saliently, the Duo language by Klaus Ostermann, and Code Scheme, also actually presented, was it yesterday or the day before? I think it was yesterday, and then also mentioned here today by Paul Downen. Can you read that? No. Is there any way we can adjust the contrast? We might have to do that. If I move the mouse, is that? No.
Potentially easy thing is to go to your accessibility settings and invert colors.
We could do that. Could you?
Yes.
You go ahead and try. Yeah, just escape and then
I stopped the presentation.
accessibility settings. Yeah, but
But once you start it, and it's like,
it depends on how much black is on the screen is the problem.
the accessibility settings.
Of the display, not the presentation.
Okay.
I guess here? No. Where is it?
Okay. Color filter.
Oh, inverted, yeah.
Okay. 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 Try. All right. We shall see how these colors turn out. See, I want to go back to slideshow, and then from current slide. And then, okay. The colors are going to be, other colors are going to be weird, but most of it's black and white, so hopefully it's okay. Okay. All right, so we were talking about mu calculus. So I want to give you a crash course on mu calculus from the perspective of a programmer. Because if you try to read those mu calculus papers, if you're anything like me, they're a little bit hard to parse. This is going to involve crunching through a lot of code. And I do apologize for that, but hopefully you can start to at least get an orientation of how these things work. Now I'm going to present this from the perspective of a puzzle. There's actually an oddity. If we're operating in a language where we have algebraic data types, there's a weird asymmetry that's happening. So, for example, consider if we have the pair data type, we have the constructor on the left, we have the destructor in the middle. In the pair data type, the constructor forms two sub-expressions. The destructor, it has a scrutiny, it has a couple of variable bindings, and then it has a body. And when we evaluate to this body with the variable substituted by the two forms. Same thing happens for the sum types. We have left and right. We just now have two different branches. Same thing happens for list. This is generalization of all the others. So lambda is a constructor, so it should follow the same pattern, right? No. Lambda, being a constructor, shouldn't have variables in it, but it does. And the thing it evaluates to is the body of the lambda, not the body of the application, which is the destructor. There's something weird going on here. So I want to propose, I'm going to evolve this language into something closer to the dual calculus, which will resolve this oddity. So I'm going to work through this example using the list case. So the first thing I'm going to do is, well, there's already an asymmetry, because eventually the goal of dual calculus is that everything that happens in expression land happens in continuation land and vice versa. There's already an asymmetry in that expressions, they just produce a value. But the constructors, they just produce a value. The destructors, they don't just destruct a value, they say which value they're destructing. Because up here we have case of E. It's not just a destruction. So we're going to erase that. And when we erase that, I'm also going to rename case to mu, because that turns out to be the operator that it actually is. However, once I've done that, now I need a way to connect constructors to destructors. And the way to do that is with a command. That command is this angle brackets form, which, by the way, is a very unergonomic notation. But in order to make it easy for you to spot where it is and for consistency, just with past papers, just for the sake of the presentation, I am going to use the angle brackets. And so the idea here is that if I take the E, either of the E's I have here on the left, I take this new C, which you might notice is actually going to end up being a continuation eventually, and I take this C and I plug the two together, then they would evaluate using exactly the same evaluation rule I had before. However, in order to, and I'm not going to justify this, just trust me, this is where it ends up going. In order to make everything fully symmetric, I cannot say that the body of a destructor is an expression, because that would be unfair to continuations. So the body of a destructor is actually, a command. It's a pair of two sides. And that gives me the options to be able to choose, am I going to talk in expression terminology or in continuation terminology? Now, what happens as a result of this? Yeah, just double checking. I thought I mixed up these slides. What happens as a result of this is everything I had before, it follows the exact same pattern, except now we have no scrutinies in the destructors, and our bodies are commands instead of terms. And then when I go to mu, something interesting happens. It turns out lambda indeed is a destructor, but it's a destructor of a constructor in the continuation world. Basically what's happening is when I do a call, I'm constructing the call stack in that I'm pairing up the argument A with the continuation K. And then what Lambda is doing is it's actually just a destructor of that call stack, and thus gets an argument X, a parameter X, and a parameter K that it then calls off to. It's all CPS. But what this also allows me to do is generalize the notion of functions, because now functions are no longer built in. We have a Turing-complete language without Lambda. Instead, it's based on construction and destruction. Lambdas are merely a user-defined data type of one type of constructor. But I could do it with other types of constructors. I've done it with pairs. Well, if I move to tuples, well, I can have multiple arguments, but I can also have multiple continuation arguments, multiple different stacks that I'm returning to. If I look at sums, I basically get case lambda because I have multiple different branches to go to. If I do this for trees, well, I don't know what that produces because I'm not able to program in this language because it's just the calculus right now. Another element that shows up here, because I want to show you what the true mu here, this is not exactly the standard mu. When you have pattern matching, you frequently have also a nested form for the pattern matching. And if you have a nested form, you also have the degenerate form, where you're not pattern matching a constructor, you're just pattern matching a variable. Well, if you do that for mu, well, what does E mu xq evaluate to? Well, if you follow the evaluation rules, it evaluates the q with x replaced with e. This is let. Okay, well, I can do everything on one side that I can do on the other, so what happens if I swap the two sides? This is let cc. So the interesting thing about this, about mu calculus, is that whereas lambda, I'm making functions my primitive, and data types are constructed in the form of church encodings. In the dual calculus, data is my primitive, and functions are constructed. There are a few tricks that we can have that pop up out of here. For example, in dual calculi, it is very normal to any time I have some expression, let's say there's an integer I'm supposed to produce. Instead, I could perform an eta expansion on mu and say, I don't want to produce that right now. Instead, I'm going to go off and do whatever I want. I'm going to hold on to a continuation, so maybe later I will decide to invoke k, and when I invoke k, that will return the value that you were expecting for e. And so it gives me more flexibility in terms of where I flow with my code. I will mention one major limitation of this system, and if you do attempt to explore this space, this is going to be perhaps the largest hurdle to making it ergonomic, which is that if I have something that in the lambda calculus would just be simply 3 function calls, I get something about like this. Now there's actually two different versions of this. The one above is a little bit simpler, but it ends up reversing the order of f, g, and h. If I want to preserve the order of f, g, and h, I have to do a more complicated construction. Now, that's actually one of the nice things about the mu calculus is I can reorder things in lots of interesting ways. But this is very unergonomic. So this is a place where developing syntactic sugar in order to be able to more easily express these things would be very useful. And the big thing is I can show you some simple examples. But when they developed Scheme, very quickly people learned, started writing code, and they started to notice patterns in the code. And they said, oh, let's abstract this out into the map function. Let's abstract this out into the fold function. We have not gotten to that point yet. In fact, I tell my students that this stuff is so early that simply the act of writing code in this type of language is research, because you will find patterns, and finding those patterns are useful idioms that will help us move forward. Okay, so I hope I've convinced you that it is possible to treat continuations as first-class citizens, but also that this is a place that needs lots of experimentation, needs people to explore the space. Okay, very quickly, because I think I'm basically out of time. Actually, we go to 5:30, right? Yes, okay. So I'm not basically out of time. I'm close to out of time. Very quickly, I want to go over a few other concepts. One is that as currently implemented, macro patterns have a little bit of a problem. If you look at let star, fairly simple implementation, the way it works is by unraveling one layer of let through each expansion. Well, the problem with this is that up here in my let star, I implemented a dot, dot, dot. And that dot, 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 every time I do a macro expansion, is checking the entire list to make sure it's a list of lists of 2 elements. That takes linear time, and I have a linear number of expansions. Let star is quadratic. There are lots of other places where macros could end up having this. Now, the right way to handle this is instead of writing this, what I should write instead is not do that pair check. In fact, when I first wrote these slides, I thought this was the correct solution, but it turns out there's even a problem with this. Because the dot, dot, dot is checking that it's a proper list, namely that it ends with a null. So the correct way to actually handle this is I have to do a full dot. This is a little bit of a problem because macro developers are being tempted into producing unperformant code if they're not aware. But even worse than that is error messages. Because if I do this sort of a system and I introduce a bug, I have the bug there, I'm going to get an error message that says invalid syntax, let star bug. Well, as a user, I never wrote let star bug, so why are you blaming me for doing that? Now, for something this small, you can probably spot it, but you can see how in a bigger language this is a bit of a problem. The traditional solution to this is that when you write let star, you have to write 2 versions of the macro. The first version of the macro goes through the entire syntax and checks that the syntax is correct, and then the second version of the macro does the actual expansion process. But what would be far better is if we had context-free grammars for S expressions. And it turns out there's a formalism for exactly that. By the way, this is one of those topics. This is my #1 topic that is not taught in undergraduates, but I think should, which is tree automata. Just as finite state automata allow us to understand a large number of categories of problems, understanding tree automata, and you only need to read the first chapter of this book, by the way, understanding tree automata is very valuable for doing that as well. You can find this book available online, tata.pdf. You might also have to put tree automata in it so you don't have to remember the entire title, but you can, it's very fantastic work, very nice properties. Now, there are systems like syntax parse that already sort of approach that, but even they do not do everything that is capable with tree automata, because it turns out that there are linear time parsing algorithms for tree automata. So I could have taken my original definition of tree automata, my original definition of let star, and through the parsing algorithms of tree automata, get a linear time algorithm out of it. However, there is still research to be done there because those algorithms were not considering macro hygiene. So once you throw in marks and substitutions, it might mess up some of the caching that those algorithms do with. So there's research to be done there. All right, next topic, readable exceptions. Exceptions are supposed to make error handling easier. And yes, it makes it easier for the programmer, but this is not a message I want to show to the user. Instead, I should be showing a message more like this. Well, how about we add a block statement? And all I ask with the block statement is that you describe what that block of code does. I've done this in my own projects, and the error messages that come out, I was frankly surprised at how nice they are when they come back out. In addition, it actually encouraged me to document my code more, because comments were not simply, because comments now had semantic meaning. Because these basically act as a comment that documents the rest of the code, rather than a comment that doesn't affect the execution. It also provided a focus of what should go here is exactly what to a user would be a user understandable description of this piece of code. As I think has been hinted at a few times today, continuations of macro expansion, or actually after I prepared these slides, it's become more apparent that being able to inspect the context in which a macro is expanding might be useful. For example, in the context of running a parser, sorry, not a parser, a prover, it would be useful to know the context in which you're expanding because that tells you what rules you ought to be applying. By the way, this also relates to the dual calculus again, because I don't know what a macro expander in the dual calculus looks like because continuations are everywhere. So there'll be something interesting there. Finally, programming with graphs. We have constructs for programming with arrays. It's iteration. Okay, I know we don't like that as functional programmers, but it is the appropriate thing for arrays. For trees, we have recursion. But for graphs, we don't necessarily have very good approaches. If you try to write a graph algorithm, it ends up looking like this, despite the fact that there's only 2 lines there that actually matter. I should not have to write all of the other lines. Me and my team are working on developing this. We have the concept of fixed point oriented programming, in which you can write simply the 2 lines that matter. One is about distances adding up together, and the other is the fact of what order you should apply the rules in, and it will generate all of the other code. We refer to this as fixed point oriented programming, and I will note we are still looking for a name for that language, because naming things in computer science is hard. Now, despite the fact that we are working on this and we have our approach, I do want to point out the broader perspective that there seem to be some missing language constructs for graphs. And I would encourage people to think about how would I want to write an algorithm that manipulates graphs. And I will also note that the work that we're doing does have some interactions with the fixed point side and the functional side, but there is some more interaction to happen there. So, in conclusion, I hope to have shared with you, and I hope you do steal. I guess I'm not sharing with you. I hope you will steal these ideas from me. Developing debuggable languages, it's that 80-20 thing. Perhaps one of the more important aspects of the design of a language is how debuggable it is. And I think that's something that we've ignored overall. Continuations should be treated as first-class citizens, not just first-class values. And then there's a whole bunch of other things that I'd be happy to talk with you if you have any questions. Thank you.
So thank you for your talk, for your interesting ideas. Regarding the debuggability, what I struggle most with is designing debuggers for declarative languages. So say a debugger of a parser generator or a query language or whatever. Do you have thoughts on how to cover that design space?
I would say that and this is borrowing an idea from Brett Victor, which is the first thing you want to do with a debugger is figure out what are the pictures that you already have in your head of your code, and make your debugger actually show you those pictures. Another element, and this is something I emphasize with my students when I give the lecture on debugging, is the most important part of debugging isn't actually figuring out what's wrong with the code. The code is doing what you told it to. And And the problem is that there must be something I'm misunderstanding about my code, because otherwise the code would do what I expect it to. So I want to design a debugger in such a way that it makes it possible for me to figure out where is the divergence between what the code actually does and what I think it does. And so this ties back to that idea of make the debugger visualize what is actually happening. So you have a picture in your head of what happens. Make the debugger generate that same picture in a way that you can start to notice where those 2 pictures differ.
Okay, but as a language designer, I think the picture that you have in mind is typically influenced by the technology that you use in your head. If you building a constraint solver, you know all the unification variables. Your end users typically don't. How would you bridge that gap? And that's a big question, I know.
It is a big question. And I think there might be a lot of different answers. And this is an area where you need a lot of people exploring different ones. And some of them will work and some of them won't. It also is, if you can make your debugger something that your users can develop and extend, then they will naturally build the pictures that they have in their mind. And so being able to try to find the pictures that are, and by users I assume you mean programmers, not language designers. But try to find the pictures that the programmers would have. What is the semantics that they have in their head? But it also works the other direction around, because if you provide a debugger that provides the semantics that you as a language designer have in your head, then when the users load their debugger, you're teaching your users what the correct semantics of the language is. So you can use that as well. These are just some random ideas.
I see. Thank you.
Hi. I was wondering, another question on the debuggable languages idea. There seem to be 2 large points in the solution space that incorporate ideas that you mentioned. The first being the common Lisp debugger, which is very much built into the language in the same way of the debug statement that you had provided. And the second, especially with that notion of pictures, is the glamorous toolkit, which is based on the Smalltalk environment and also has a built-in debugger notion that allows you to kind of have this picture of here is what this thing is doing, not at a exception and programming language value level, but at a semantic level of here's what I'm thinking about in terms of language design. Would you say that either of those completely or cover a sufficient space of the debuggable language question that you're asking about, or do you think there's like a different dimension that they're not exploring?
So first I have to say I'm not familiar with either of those systems. I've heard legend of them, but somewhere along the line, regardless of the legend, that functionality seems to have been dropped. I would say that there are at least two elements that perhaps could go beyond them. One is to ensure that they are something extensible. It's not just a static artifact. It's something that users can add, experiment, develop higher levels of abstraction on top of the debugger. The other is debuggable languages isn't just developing a debugger. There's many other elements which I did not discuss about what does it take to make a good debuggable language. Part of the reason I didn't discuss those is I don't know what those aspects are. That's something that needs more attention and more exploration. But yes, I think those would probably be very good places to start to look for something that we could mine and build upon.
Great, thank you.
In my opinion, I think what you're saying is to design a debugger, you need to open up the semantics of the language, and I think where you are headed is that I think that leads to reflective languages, and I wonder if you have any comments on that. So reflective language tries to open its semantics to the user so that you can tweak into the semantics. And well, if you change it, then that's quite radical. But if you just observe the semantics, then I think you will have enough information to do various kinds of debugging. So, well, reflective language is not right now very popular, but if you can resurrect that, then I'm very happy to.
Yeah, it sounds like something that would be applicable. I don't have many comments on that other than please go explore, build.
Well, I have a lot of things to tell you.
More quick.
So the large theme of this talk was ergonomics. I'm kind of curious. Maybe it kind of just went over my head a lot, along with the rest of the mu calculus. What do you find to be in your opinion, going to be the largest ergonomic benefit from the mu calculus?
The largest ergonomic benefit is that currently we're only operating within the land of expressions. Doing anything with continuations is considered weird, unintuitive, hard to visualize. However, everything that exists within expressions also exists within continuations. There's a complete formal dual. As a consequence of this, right now, effectively, we're all breathing with only one lung. We're only programming in the expression land. There is a whole other world out there to be discovered and learned. Concepts such as double-barreled continuations or success and failure continuations. Things like, I'm going to borrow something from the Haskell world, people understand monads, but they don't understand comonads. Hopefully, the idea with a dual calculus is every time you learn one thing, you're actually learning two things. Hopefully, concepts such as comonads, co-induction, these sorts of things, and I don't know, this is just a hypothesis, will suddenly become obvious and easy once that duality is fully exposed. That's one of the things I hope we'll see whether that pays out.
Thank you.
Other questions? Good. because I have a question.
Okay.
So language and thoughts, okay? To debug things, you have to have a language to express them. So the first thing to do is to make people think in terms of the lambda mu tilde calculus. And once they can, when they have been talking about that and thinking about that, then they have the linguistic infrastructure to identify what's going on and to be able to read what's going on. That was a comment, not a question. I'm so sorry. And another one about usability of debuggers, the economics part. I was very impressed by an old colleague at Aarhus University, Susan Böttcher. She got awards at SEM not long ago. And the way she worked a lot on debuggers, and she's in human computing interaction. And so what she did was really amazing, because she put a camera next to the computer that people were using at the time, and then she recorded what they were doing, and then she studied what they were doing, and then she improved the debugger. So there is the observation aspect that will feed back on the actual design. So listening to the users, seeing how they do that. But that's kind of tied to the language and thought idea. Once people start to think the way you want them to think, well, then they express their thoughts in a language, and that language will be corresponding to the notion of computation that you want. So introducing so there are two aspects: the temporal aspect, how they use it, and then there is the semantic aspect, what they think and how they express that. So I will second the question. How do you think in the lambda mu tilde calculus?
Okay. That's not the direction I thought you were going. I will comment on your comment before answering the question, which is those user experience surveys are very much in line with at the beginning. I mentioned the book about the best way to learn ergonomics is to actually try it and see what people end up doing. And we don't do that so much in programming languages for multiple reasons. But even just doing that ourselves, releasing a library and letting it out into the wild and saying, hey, I think this is a good thing, and coming back 2 years later and see whether people use it. In itself, even if we're not doing a formal human factors user study, is a form of user study that we can do. And I think that's where a lot of things can be developed. How do I think about the mu calculus? I don't know. I know that I do. I have an intuition, but I will have to spend some more time of thinking about it. Well, okay. Here is, I could spend 10 minutes talking on this. I'm going to try to give the shortest version possible. The way that I think of it is that expressions are things that produce values. Well, actually, let me take a step back. Think about functions. Functions take an argument in and they produce a value back out. Imagine if you'd taken a function and cut them in half. So expressions are that second half. They produce a value, but you never ask the question, yeah, but what was the argument that the expression used to produce that value? It produces the value by combining some variables and some constructors and whatever, but it just produces a value. It doesn't consume a value. In the mu calculus and in continuations, the mu forms just consume a value. They never produce a value. The thing people always ask is like, okay, it takes a value, but then what does it return? The answer is it doesn't. And part of the reason is because the reason it doesn't is it goes off into other covariables. And so I think of expressions as like this hose that's spitting out values, and mus as this hose that's sucking in values. And so when I do a command, I'm plugging the two together. And the surprising thing is that I no longer have the ends of any hoses left. So that in itself, the commands, they don't return a value, which is perhaps one of the most surprising things people find. It's just that now these variables are connected to those variables. So that's one of the aspects I'm thinking in terms of I'm plugging things together. And they come from some place and they go off to some other place. And I'm grabbing the continuations and other things. I'd have to spend some more time, but that's one of the insights I've had.
So you're thinking in big terms, in big step terms, not in small steps as induced by the calculus.
That's an interesting statement, because in the mu calculus, big step is small step. because the mu calculus looks a lot like, the underlying calculus looks a lot like a machine already. So even if I try to be big step, I'm actually also small step.
Fair enough. Okay. Now, there's a pre-linguistic aspect to computation, is to just thinking computationally. So I'll give you a very concrete example. I waited my whole life her own life that my daughter asked me how to program. But I fed her during a whole upbringing with logical and algorithmic games. And so when she asked, she was ripe. Now consider that when the kids who are being taught, here is how to use a computer, they have no computational thoughts. And so they are introduced in a language, weird ergonomics to do something that they have no thoughts about. And when you have nothing to think about, well, the language that you're exposed to is kind of empty. So that's why my question about how do you think should like predate how you program is a what and how, language and thought again. So thinking computationally would be the prerequisite, and once you have some thoughts, then a language in which to express them kind of comes naturally.
I would push back on that a little bit because of the stage of development of the community's understanding of the system. It's sort of just like after lambda calculus had come out. Eventually, we're going to figure out what the right way it is to think computationally about this, but we are still having to figure that part out. So we have to present the language. Lots of people are going to try to figure out how to think about it, and hopefully they share those ideas with each other so we can start to develop how do we think about it. I gave you the analogy with hoses, but there might be better ways to think about it. Eventually, once we get this built up, of that this is just a normal part, just as normal as the lambda calculus. You should expect people to understand it just as much as the lambda calculus. At that point, then I think we can start to think more in terms of here's how you do computational thinking, and then add these linguistic aspects. But we are very early days in that regard.
But then about the lambda calculus, I mean, the lambda calculus is really big on substitution. There is no substitution in implementations, they're environments. So that means that all the time that we spend explaining substitutions is for nothing because it's never reused. And it's only useful if you reuse it. And substitution is never reused. So most of the time we spend on the lambda calculus is wasted.
It was a bootstrap to be able to understand evaluation styles, or using environments, for example.
But then why didn't you have a calculus of explicit substitutions where there is no substitution, there is the term and then its bindings? Then people understand closure at the calculus level.
I'm not sure how to answer that one. I think there's a lot of things to be explored here. It's the main message, I think.
Yeah. Thank you. Any other questions?
Could you go back to the slide with the Dijkstra algorithm?
Yes.
Okay. Thank you. Yes. Yeah. What happens? So you said that these are the only two things that need to be replaced. All the other stuff is. What happens if you replace them with something else? What happens if you use a first in, first out queue?
The asymptotic performance isn't what you want.
Yeah, sure, exactly. Yeah, but okay, but you get the wrong result as well, don't you? You don't get the shortest distance.
No, you should still get the same result.
Okay. What happens if you replace it with D1 minus D2? Then you get the wrong result, right?
Yes, you definitely get the wrong result then.
I'm just curious as what class of algorithms come out of that way of looking at things?
Well, it's work queue algorithms. Work queue algorithm, work list algorithms, parsing, static analysis, type checking, most graph algorithms. There's a large number of algorithms. But anytime you're writing a work queue, it'd be much better to write it like this than the other way around. But we're developing languages to be able to do that.
Okay. Last chance. Let's just thank our speaker.
that concludes this year's Scheme workshop. So thank you all for coming.